Hello, this is Mr. Wynn, and this video is over common logarithms and solving exponential equations and inequalities. So first, remember that all logs must have a base. The most common log base is 10. Base 10 logs are called common logarithms. Since it is used so much, it is the default log in the calculator, and if you don't see a base next to log, it is automatically an invisible 10. So right here it says log base 10 of x is literally the same thing as log of x. The 10 is invisible. And that's for all x is greater than 0, because you cannot log 0 or a negative number. Alright, so in the calculator, this right here, this log button on the very front, that is exclusively used for log base 10. Underneath that, they have ln, that is exclusively used for base e. And when we do any base we want, make sure you press the math button, press up, go to log base, and you type in whatever base you want. Alright, on the left, I do have the graph of f of x equals log base 10 of x, again the 10 is invisible. And the next I have f of x equals log base 2 of x. Notice the graphs are a little different. When it's a smaller than 10 base, the graph goes kind of higher. Alright, but they both go through the point 1, 0. Alright, because the log of 1, log of any base of 1 is always going to give you 0. And if you use the differential logarithm, that's saying anything to the 0th to the power equals 1. Alright, now notice the log graph is the inverse of an exponential graph. Inverses, again, are found by switching x and y and solving for the new y. It will always have a vertical asymptote of VA, that's at x equals 0, that vertical line, but no horizontal asymptote. That's the reverse of what exponential graph has. Also note that the AHK transformations still apply like on all functions. A is going to be flip or not, vertically stretch, vertically compress. H is shift left to right, K is shift up and down. Also remember H is opposite. Alright, if you apply the differential logarithms, aka the conversion trick, you can quickly see that all these things are true. If you have log of x equals y, that means 10 to the y equals x. Because if I do base 10 exponential both sides right here, notice x equals 10 to the y. I know they write it backwards, but this is literally the same thing. 10 to the y equals x. Alright, then here's some other facts that we know. Log of 1 has to equal 0. Why is that? If I do base 10 here, exponentiate, this gets out, we get 1 equals 10 to the 0 power. Y'all know any number to the 0 power equals 1. So that right there is true. Alright, next one. Log base 10 equals 1. Well, first off, you know these cancel out, so you know 1 equals 1. That's true. But secondly, if I do exponentiate, base 10 both sides, log 10 to exponent log 10 is gone. Otherwise, it's 10 equals 10 to the first power. We know that first power is usually invisible. There's that. Then last one, log of 10 to the m power equals m. Well, 1, you could cross this out, so m equals m. 2, you could actually move this to the front exponent rules and say, and this crosses out, it's 1. So m times 1, so m equals m. Or 3, exponentiate both sides base 10. These cancel out. You have 10 to the m power equals 10 to the m power. Alright, so as long as you know how to do definition of logs, meaning the conversion trick, if it's one term both sides, know how to log both sides with a certain base, or exponentiate both sides with a certain base, you're good. Alright, now let's try some solving. So solve exponential equations by making x no longer an exponent, by logging both sides, and then solving like normal. Remember your 3 log properties, how to move the exponent up and down, combine logs being added, and combine logs being subtracted. There's no need to check your answer, as the domain of all exponential functions are all real numbers. You can have negative exponents, positive exponents, and even an exponent of 0. Remember, a number to the 0 power is 1. So solve 4 to the x equals 19. We can't do common base like we did 4. We can't change 19 into 4 to some power. We also can't, we could change 4 into 2 squared. So it would be 2 to the 2x equals 19, but 19 can't be rewritten as 2 to some power. We must use logarithms. I'm going to do 2 methods here. I'll first use common logarithms, and then I'll use non-common logarithms. Common is the old way, but they do expect you to know it. So first, I'm going to log both sides. Alright, the moment I log both sides, some nice things happen. Exponent rule, we know that this goes down to the front. So really, this is x times log base 10 of 4 equals log base 10 of 19. Remember, log base 10 of 4 is just some number. I don't know it. No one really does. But this is basically x times some number equals another number. You're going to divide both sides by log of 4. Just cancel out, and that's your final answer. Exact answer is x equals log of 19 over log of 4. Alright, now they do want the decimal. They said round to the nearest 10,000ths. That is 4 decimal places. So I type in the calculator. Notice we get about, or approximately 2.12340. I'm looking at this fifth decimal, the 6. The 6 does bump the 9 up to 10, which bumps the 3 up to 4. Alright, so there's one side. Let's do the other side. Let's do non-common logs. So from before, I told y'all you're supposed to log both sides. But logs need a base. And unlike doing base 10, 10 doesn't really help us much. I can pick any base I want. The smart bases are 4 and 19, because that'll make one of those logs disappear. I'm actually pick 4 because that has the exponent x. When I do this cancels out. This is just x. Again, you can also just bring this to the front, your choice. Equals log base 4 of 19. I'm done. That's the exact answer. If I type that in the calculator, I get about 2.1240. Same thing. The 6 bumps that 9 up to 10, which bumps the 3 up to 4. It's the same answer. And the run on the right side is less work because I use a non-common log because that cancels out the log out. I'd rather have one log in my final answer than 2 logs or multiple logs. Alright, so using that fact, we have what we call the change of base formula because they're the same thing. That allows you to write the equivalent logarithm expression with a different base. So for all positive numbers a, b, and n, where a and b aren't 1, log base a of n is the same as log base b of n over log base b of a, where b can be any base you want. It could be base 10, could be base 100, base 1000, base 3. Alright, but make sure you know the original number goes on top. So n goes on top. And then the old base, a, goes on bottom, right here. Alright, so for example, on the right side I have log base 3 of 11 is the same thing as log base 10 of 11 over log base 10 of 3. Notice that the 11 is on top, and the 3, the old base, is on bottom. Alright, over here it says log base 450 can be written as log base any number of 50 over log base any number of 4, and that's true. As long as the 50 is on top, the original number, and the old base 4 is on bottom. So 2 quick problems. Express log base 3 of 20 in terms of common logarithms. They want base 10, so I can change this into, see, log of 20 on top, log of 3 on bottom, and they want base 10 because they want common logs, so I'll put a little 10 right here, and done. Another one says express log base 799 in terms of base 44 logs. So again, log 99 is on top, log 7 is on bottom. They want base 44, so here's the 44 base. Alright, that's it there. Alright, number 6. Solve exponential inequalities by solving like a normal exponential equation, but be careful of the inequality sign and flip it when needed. Again, that's when you multiply or divide both sides by a negative. Also know there's no need to check your answer because the domain of all exponential functions are all real numbers. You have positive exponents, negative exponents, and 0. Alright, so example 4, solve for y, round to the nearest 10,000th. I'm going to solve with both methods. So first I'm going to use common logs. Again, this is the standard way of doing it, but there's faster ways available now. The moment I log both sides, I can do a couple things. Exponents go down to the front. Exponents go down to the front. So really, this is going to be 5y times this log base 3, base 10 of 3, less than, this will be a y minus 2, times log base 10 of 7. Again, log of 3 is just a number, log 7 is just a number. This left side is good. That's 5y log 3. But over here, I have to distribute. This is 2 things times 1 thing, so I'm going to distribute like this. So I get y times log of 7 minus 2 times log of 7. Then I'm going to get y to one side. This is technically linear. I'm going to move this over to the left side by subtracting. So this is 5y log 3 minus y log 7 is less than negative 2 log 7. Alright, these things, remember, this is just 5 times some numbers. This is some number y, and then this is just some number as well. So this is y times number y. These are supposed to combine, but we don't know what those numbers are. So instead of combining them, we're actually just going to GCF the y. If I pull a y out, what's left would be 5 times log of 3 minus log of 7 is less than this. Then from here, to get y by itself, I'm going to divide both sides by a thing in parentheses. So that's 5 log 3 minus log 7. This is the exact answer. Now actually I could do some log properties. I can move this -2 right here to the top exponent of the 7. I can move this 5 to the top of the 3 if I want to. There's no need. I am going to type that in the calculator right here and see our final answer. Round to nearest 10,000th. I get this. It's about -1.0972 because it's 6, this fifth number, does bump that fourth number, that one up. Alright, so -1.0972. Alright, I'm going to solve this another way using non-common logs. When I do this, the numbers will cancel out and it will be shorter. So let me do that. So first log both sides, and now I'm going to pick a base that's not 10. I can actually pick 3 or 7. It doesn't matter. Now actually picking 7 is easier because that exponent is more complicated, but I'll do 3 just to show you what happens. So the left log cancels out. The right log is some number I'm going to have to distribute with this right here, like before. After I distribute, I have to move y to the left side. From here, this is 5y minus y times some number. That's like maybe 2y. If I did 5y minus 2y, they'd combine to 3y. But again, I don't know what the number log base 3 of 7 is. So I'm just going to GCF, factor out that y. So it'll be y times 5 minus log base 3 of 7 is less than this number. Lastly, to get y by itself, you're going to divide by that number in parentheses. Alright, so notice when I type this in the calculator, it's the same answer from before, but now instead of having 3 logs in the problem, I only have 2 logs. Now if I did base 7, here's what the answer would have been. Same number, but my final answer only had 1 log in the problem. So pick the best log, the best space, and your work will be a little easier. Now if the exponent had 2 terms on both sides, then you might have 4 logs in your final answer if you're using common logs. But you usually only have 1 or 2 logs in your final answer if you use a smart base that cancels out one of the logs. And again, this is the hard type problem. We'll do a bunch of these in class. Alright, last problem. Find the inverse of this. So again, this is exponential equation. Y equals 10 to the x power minus 1. So remember, to find inverses, you switch x and y. Well, first step is put y in there if it's not there. Step 2 is switch x and y. Step 3 is solve for y. To get y by itself, we have to bring it down from x1. We're going to log both sides. When I log both sides, I need to pick a base. I'm going to pick base 10. At the moment I pick base 10, this right here will cancel out. So I get log base 10 of x equals, technically this comes down to the front, or you can just say it's all that's left, y minus 1. To solve for y, last step is I need to add 1 to the left side. So log base 10 of x plus 1 equals y. Alright, so now I'll write it with the f inverse. So the inverse is log base 10 of x and then plus 1 on the outside. So notice the inverse of an exponential equation is indeed a logarithmic equation. That's it for the video. Thanks for watching. See you soon. Make sure you ask questions. Bye.